But like I say, we're going to treat this as an academic conference, no flowery introductions. The first speaker is Bob Willis.
Okay, I think I should finish by 1:30. I'm really happy to be here, and I want to acknowledge Don Carr, who's one of the lead author on this paper, is in the audience, and the other co-authors here are not, but I'm grateful to all of them for all of the work on this. And I'm also grateful to the Sloan Foundation for supporting this research. So I want to begin with motivation here. There are many components of cognitive ability decline with age, beginning around age 20, and continuing, unfortunately, for the rest of life. So by the time one gets to my stage of life, there's been quite a noticeable decline. The declines include fluid intelligence, which is a psychological term that largely covers people's ability to reason in unfamiliar situations, working memory that allows me to add up a couple of numbers and remember the first number till I add to the second one, and episodic memory, which is memory over a longer period of time, which is a better measure that's been used in quite a bit of the research in the health and retirement study, which I'll be using later on. The episodic memory is measured by reading people a list of words and then asking them how many they recall, and then going on with the rest of the survey, and then 10 or 15 minutes later asking, oh, I remember this list of words that I read to you, how many do you remember now? And so that's memory over a bit longer period of time. And other components. There's the use it or lose it hypothesis that's been around since probably the turn of the 20th century, a long time, that suggests that mental exercise might stave off decline. That is, many people are extremely worried about the loss of cognitive ability, and they are trying to think about almost any way that they could figure out how to stave that off. And while the lab evidence for the use it or lose it hypothesis is pretty weak, a growing body of research using population data finds that delay of retirement has a causal effect on improving cognitive performance on memory. And this evidence suggests that the work environment is more mentally stimulating than the home environment, or possibly that the expectation of retirement reduces the incentive of workers to exert the mental effort to maintain their skills and cope with other challenges at work. So Suzanne Rowader, who's over here, and I did a paper which was entitled Mental Retirement, and I'm not going to go through our stuff, but basically what we did is we used cross-national data to try to establish a causal story. If you look at this left-hand picture, this shows the correlation between the average memory score that people have and the percent of people who are working for pay, and this comes from means and microdata from these health and retirement study in the United States, the English longitudinal study of aging in England, and the survey of health, aging, and retirement in Europe. And you see a pretty strong negative correlation there between these two variables, and the question that we addressed was whether that is, what's the causation here, and we made use of other work by John Gruber and David Wise, and the big MBR project basically showed that labor force participation varies across these same countries, largely because of the role of economic policies that the different countries have that created different incentives to retire. And we made use of these policy difference to do an instrumental variable estimate of this relationship, and we ended up with a pretty sizable negative effect of retirement on cognition. And so there's been other work that's been done largely using either, the data sets that I've already talked about that support this sort of mental retirement effect in other papers. And I think it's now becoming relatively well established that this kind of effect seems to be there. But there's really need for better understanding of the mechanism underlying the effect. Sort of what is it that's responsible for this effect? And there's some recent studies in examining the complexity of work that show some promising leads. There's a Swedish adoption twin study that found people in occupations with high engagement with people build up verbal skills faster during work, but then lost them faster once they retired. That suggests that taking away work from lifestyle is a key element in mental exercise. Gwen Fisher, who's here, and her colleagues find that those in more mentally demanding jobs in the HRS had a higher cognitive function prior to retirement, experienced less decline in cognitive performance following retirement, and that suggests that cognitive complexity may generate cognitive resilience. A study by Kachitani and company found men in careers in Japan that required high mathematical reasoning, language development experience, less decline in memory following retirement. So one thing that we have wanted to do in the paper, the mental retirement paper that Suzanne and I did, we just lumped everybody in the population together and didn't distinguish what kind of work they were doing, although much of our discussion was really based on the notion that there are kind of really two hypotheses here. One is the sort of psychological hypothesis that says that mental exercise might influence your cognitive ability or your stave off cognitive decline. And the second is a hypothesis that there's a differential degree of stimulation or occasion for mental exercise in work versus, say, non-work that leads to these kinds of effects. And so it makes sense, and I'll end a little bit by saying it would be worthwhile looking at the home environment more carefully than studies have done. We won't do that here. But also, it seemed worthwhile to look more carefully at the work environment. So the goals of this paper are to use a counterfactual econometric framework to estimate the effect on cognitive change over a 6-year time span in the health and retirement study of full retirement versus continued full work for workers whose jobs differ in intellectual and mechanical complexity. And we want to interpret, and we're going to interpret our results in terms of a new psychological theory that has the acronym STACK that I'll tell you a little bit about that in a moment. So the idea here is that we want to sort of look at the effects of different kinds of jobs. We don't really have available instrumental variable that would help us too much on this problem, and so we're going to be using a kind of econometric technology that has been used a lot in the evaluation literature and on policy evaluations and sort of naturalistic, randomized trial kinds of things. And whether this approach may be, I think we need to be cautious about sort of taking it literally, because it may or may not be getting what we want. But I'll talk about that a little bit later. Okay, so what's STACK? STACK is called the Scaffolding Theory of Aging and Cognition, and it's a relatively recent proposal that starts with this idea that I've already mentioned, that many cognitive functions decline with time. And two psychologists, Denise Park and Patricia Reuter-Lorenz, said, well, really the kind of interesting question that comes out of this is, why is it that older people tend to be able to function pretty well? And I'm a fan of that view. That they're able to function quite well despite these declines. And what their argument is, and they provide argument from sort of the neuro side of evidence, that there's something that they call compensatory scaffolding. Scaffolding by them is defined as the recruitment of additional circuitry in the brain that shores up deteriorating components. And scaffolding occurs in new learning and is also in less novel or practiced behaviors. They've done they had a project that did a randomized trial on trying to give people extended, concentrated tasks, like learning how to use electronic photography and manipulate the pictures in a detailed way, that was sustained over 3 months. And they found some evidence in favor of this scaffolding theory. Well, one of the things, this is actually, I'd seen a paper on this about 10 years ago that kind of inspired me, and is actually apparently more evidence on this is accumulated. If you give young people, say a 20-year-old, a new difficult problem to solve, and you put them in an fMRI situation so you can watch the kind of neural response, what happens is kind of what you'd expect to happen. Their left frontal lobe lights up, and they are grinding away, figuring out, I don't know how to do this, but I can reason my way and get to a solution. If you give the same problem to an older person, and I think the data I first saw, the older person was just defined as quite a bit younger than I am, like about mid-50s. What happens is that the left frontal lobe lights up when they see this problem, but the right lobe also lights up. And the interpretation of this is that what's happening is that you're going to, or my first intuition, it's like saying, well, look, I can't solve this problem that I once could solve when I was a college freshman. My reasoning ability is not that good anymore. My ability to concentrate is not that good anymore, and so on and so forth. On the other hand, I've seen problems like this. And even though I can't solve it, it must be up there in that in the book in the shelf, or even better, it might be sitting somewhere in my brain where I've seen this before. And what I do then when I'm confronted with that problem is I retrieve this other solution, but I still have to reason about it. So both, it's not one or the other, it's the two are combining. And what the stack theory is saying is that when that happens, that establishes a connection. There's now a connection between that problem and this knowledge that I've brought to bear on that problem. And as we get older, while our reasoning ability is falling, our knowledge is increasing, and this is compensating for this. So that's sort of the idea. They also showed that higher performing older adults show more bilateral activity. That's the name they use for this firing up in both right and left lobes. And it suggests that higher cognitive ability leads to more scaffolding. That is, there's more connection being built. This is a sort of picture of their theory, which I think I'm not going to go through, but it just does more or less what I suggested. I have long felt that there's a very strong connection between the theories that are being developed in psychology and in neuroscience, I should add to, and human capital theory. Human capital theory suggests that an individual's productivity in any particular activity depends on both their reasoning ability and their knowledge. So we could call GF fluid intelligence, and GC is what's known as crystallized intelligence. That's my knowledge. And the human capital theory would suggest that GF and GC tend to be complementary. That is, my ability to make use of my knowledge is enhanced if I'm a better reasoner, if my reasoning ability is higher, but my reasoning ability is enhanced if I know more. Reasoning in a complete vacuum is actually not a terribly productive activity, I guess, except perhaps in pure mathematics. The later in life accumulated knowledge increases the productivity of a person who's, so early in life, this learning activity goes on through schooling and job experience and other things. In other words, you spend a lot of your time early in life using your reasoning ability to build durable knowledge that you will use in your job and your home and wherever. And later in life, accumulated knowledge increases the productivity of a person whose reasoning ability has declined. So the stack suggests the neural circuitry then really connects GF and GC, and I want to move on, I think. So in this paper, we use data from the HRS to examine the effects of occupational complexity on cognitive change. And we're going to use a measure of cognitive change that's mostly made up of this episodic memory, but it adds some working memory elements and processing speed elements to it. And is a trio of tests here that have been used widely in the HRS and have a sort of fairly standard interpretation within the cognitive psychology literature. And our dependent variable is the change in the cognition score between when people first come into the health and retirement study and then 6 years later after they've been. So we're going to be looking at cognitive change probably more than at cognitive level. So the sample definition that we're going to be using is we're going to, here's time 1, so that's when people enter, and we're trying to set this up so that we get as extreme changes in sort of the environments that people face as we can get. So we're concentrating on people who are full-time workers at the baseline. In a conversation we had, several of us had at an advisory committee meeting this morning, there are a lot of people who are not working full-time even at fairly early points in the survey. So we're excluding some people who we might be interested in later. And we also have excluded people who start at baseline with really low cognitive scores because we want them to be in sort of the normal range of cognition. And then we're going to make sure that the first group is people who work full-time for 2 waves and then retire fully in time 3 and stay fully retired in time 4. So that's one group. And the second group are people who are working full-time all the way through. So let me talk a little bit about job complexity. Characteristics of jobs have been coded by the U.S. Department of Labor in ONET. We have used a crosswalk between HRS census-based occupation codes and ONET standard occupation codes that were kindly provided to us by Peter Hurd, who's also in the room, to link ONET and HRS data. So this is a large slide, but it's basically the ONET, when you look at it, produces this overwhelming amount of classification of jobs into 3 broad categories of abilities, activities, and contexts. So abilities are deductive reasoning, inductive reasoning, mathematical reasoning, arm-hand steadiness, finger dexterity, multi-limb coordination. The activities are getting information, inspecting equipment structures, blah, blah, blah. Context, face-to-face discussions, coordinate or lead others, spend time making repetitive motions, blah, blah, blah. So there are lots and lots of characteristics, more characteristics than people perhaps. And so one really has to boil the data down in some way. And the boiling here took down to really two components of intellectual and mechanical complexity of the occupation. Don will be the one who will have to answer questions about exactly what went into this. And so we have 2 categories. One was we call intellectual complexity items, and they include the making decisions, thinking creatively, coaching, developing others, frequency of decision-making, freedom to make decisions. And a second set of things that we analyze separately is mechanical complexity items, inspecting equipment, structure, material, handling and moving objects, controlling machines and processes, and so forth. And what the coding does is it allows you to say on either one of those dimensions, which are also chosen to be more or less orthogonal to one another, that they could fall into very very intensive on that dimension or very non-intensive, and we've divided things into sort of low, median, and high terciles of that. This gives you sort of, again, I think I won't spend time on it, but kind of here are the detailed occupations, and the yellow shows sort of the occupations that are sort of most frequent or largest in each of these categories. So professionals are moderate intellectuals, and managers are more highly intellectual. So I've got to go fast because I've got. So we have complexity and job scores. I won't go through that. An analytic approach, we seek to answer a counterfactual question. What would happen to the cognitive trajectory of a person who's given the given degree of complexity who retires fully compared to the trajectory they would have experienced had they been working full time? And it's clearly impossible to answer that question at the level of the individual because the person either does or doesn't do that. Put differently, this question inherently involves treating the outcome variables missing for the counterfactual condition. And the best we can do is estimate the mean trajectory of a group of people who did retire compared to the trajectory of similar people who continued to work. And an obvious challenge is that people choose their occupation, and they also choose whether or not to retire. And because of self-selection, comparisons of mean outcomes may be biased because of the comparison groups differ. One approach to this challenge is to use IV methods. As I mentioned, we can't. So the approach that we're using is something called an inverse probability weighted regression adjustment. And this is drawn from the treatment effects literature. And what you do is you have two equations. One is what's called potential outcome means, which says it's a model saying what's the relationship between the change in cognition and a set of covariates conditional on your occupation and being fully retired at times 3 and 4. That would be the outcome for people who are the retirees. And then a similar equation, change in cognition conditional on working full time. And then a second equation is a multinomial logit propensity model, which says what's the probability that a person would be in treatment as a function of a set of covariates also. And then there's an average treatment effect, which is the relationship between the two, conditional on complexity. And this yields unbiased estimates of these two concepts, the potential outcome and the average treatment effect, assuming selection on observables. That is, we ignore, also known as the assumption of ignorability and confoundedness. And we've made an attempt to include a set of covariates that make this assumption plausible. But there are many examples that you could give that would disrupt this. An individual develops a sleep disorder that reduces cognition and also increases the disutility of work, leading him to retire. Well, clearly his decline in cognition has not been caused by retirement per se. Here's a set of covariates, and I won't dwell on them other than to say they include race and education and wealth and income and age and a frailty index and change in self-rated health and frequency of moderate activity. So getting down to the end, what we see here are the estimates for changes in cognitive performance on intellectual complexity, and we see that the effects really do vary by the level of complexity. I'm just going to show it in a graph here. For the cognitive complexity, the biggest decline is for the people who are in low jobs, start in low jobs, and they suffer a substantial loss of intellectual of cognition or have cognitive change. And there's a very small effect for the people who are in the most cognitively intense jobs. And that seems consistent with what the stack theory was suggesting. We did the same thing for mechanical complexity of the occupation. We have less sense about what that's doing, and in general, the size of the effects are smaller and a little less significant, but they do show an opposite sort of trend. There's again, the people who retire or have lower cognition than the people who stay on the job, but the magnitude of the effect now is bigger for the people who are at the high end rather than the low end, and we kind of speculate that this might be due to the fact that the effects that mechanical complexity may have less transferability to the non-work environment than the intellectual complexity. So our conclusions is that, as suggested by the stack theory, that people in intellectually complex jobs seem to suffer relatively small losses of cognition when they retire, perhaps due to the development of extensive scaffolding from work that's transferable to the retirement environment where they remain intellectually active. And conversely, people in jobs with low intellectual complexity appear to suffer substantial losses in cognition, perhaps because they did not build much scaffolding during their work career and do not maintain mental exercise during retirement. And I already told you that mechanical complexity results under the assumption of selection on observables, our results can be interpreted as causal. However, there are good reasons to worry that this assumption may not hold. In particular, the basic hypotheses that maintaining mental exercise is a key to maintaining cognitive ability means that we need to explore the complexity of the home environment and how people change their non-market activities after retirement. The HRS has measures of time allocation, such as time spent watching TV, mental state, boredom, for example, that people experience both before and after retirement. We've begun to look at these, but we don't have anything really strong to say about that at this point. And finally, that there's scope for further integration of theory and measurements by economists and psychologists to advance our understanding of these things. Okay.
I will begin. The very first slide will show you my surprise. Today is Bob's birthday. So after we've had a few glasses of wine this evening, maybe I'll lead everybody in a round of happy birthday to you, Bob. Congratulations. This is the paper. We're interested in the relationship between retirement and cognition, and the language used in the authors are slightly coy, I would say, about, they only use the word causal once or twice. But if you're talking about treatment effects, then I guess you're really talking about causality, and so we would want to frame the discussion in terms of causality and see where we stand. So the treatment is, and the language comes from randomized controlled trials. The treatment here is retirement. The probability of a treatment is the propensity score, depends upon some X variables. And these, there are confounders in this, as Bob mentioned. There are variables that affect both retirement and affect cognition or cognition change. He gave some examples, but many things spring to mind having to do with health declines or latent variables that affect the ability and utility that comes from work as well as cognition. And so this is really a problem, and I would say that the required assumption for what they do is that these X's that are going to the propensity score include all the co-founders that there are. And I found it easier to think of this in the framework of regression. The requirements are basically the same to get identification here. So consider these two equations. One is cognition, depends upon retirement, some X1 variables that are control variables. The X2 variables are the confounders because those also influence retirement itself. There's the second equation is the retirement equation. I've included also something that they rule out, which is that cognition itself influences retirement. It's mentioned, but you can imagine that somebody who has a decline in cognition no longer finds it possible to work and therefore retires. So we at least want to include the idea that gamma is not zero. And then the X2 are these confounders. So what is needed here to get in the regression setup to get identification of beta, which is what we would like to know, is firstly that gamma is equal to 0, and secondly that we have data on the X2, because if we don't have data on the X2, then you can rewrite that first equation, absorbing the X2 into the epsilon now the new error term, and now, of course, retirement is correlated with the epsilon, and so least squares will not give you unbiased or consistent estimates of beta, which is what you'd like to know. And it was because of these ideas, the suspicion that gamma is not equal to 0 and that x1 is not fully observed. I mean, there are a lot of candidates for confounders that led to the instrumental variable approach that was used by Roveder and Willis, who were major founders of this line of work, following work by Perelman in the famous Perelman graph that was first unveiled at a conference at Rand some years ago. So what I thought I would do, I find this topic really interesting, so I thought and I expect, hope the audience does also, was to look at some patterns in the data that lend support or subtract from plausibility to the assumptions of the paper. And my guess is that most people in the audience don't know what those patterns are. So I thought we would spend some time looking at those. I've known Bob for many, many years, and I know in paper presentations, these kinds of things are too simple for him, and he never presents these kinds of things. I knew there would be no. So here are the cognition scores, the same variable. I used ages 51 to 68. And to give an idea of what the scaling is, I show you the average cognition scores in this sample, age 51 to 68 by high school level, less than high school, and college graduates. So you can see that, say a score of 1, an increase takes someone from the high school level to having some college. So you might think an increase of score of 1 is a fairly, it's not negligible. And so it'll give you some idea of what the metric is. Now look at changes in scores and baseline associated with transitions from work to work, work to not work to work, and not work to not work. And look at cognitive scores before and after those transitions. So first, these are just cross-sections of two groups. The top are those people who are working, and the bottom is those people who are not working, and the line in the middle is the cross-section average. And what you see here is that people who don't work at age 51 have cognition scores that are 2 points below people who work. So they start out in very different levels. Those lines kind of narrow, but that's partly due to selection. I'll talk a little bit about that. But you begin by seeing very large differences, more than the 1 point that I said might be important. So very large changes. This graph shows the same two things on the top and the bottom, but in the middle is the cognition scores of people who transit from working to not working, and the scores recorded before the transition. So these people, when you see that score, they're working, and then in the following wave, they're not working. So what you see there is that people who transit from working to not working had lower scores before they transited. And so you obviously cannot compare levels here very easily. You're going to have to look at rates of change, and even then you can see there's a fair amount of selection going on here. One thing that is not in this paper, and I looked at, and this could provide something for future work. Now the top and bottom lines are the same as before, but the red line is the score of people who transit from not work into work while they were not working. And you can see these people who went back to work actually had high scores about as high as people who were working prior to that. And I think that group may be the subject of some interesting future work. I mean, what happens to them? Once they go back to work and they have this forcing function of cognitive stimulus, do they continue to do better? So, but I'm not pursuing that today. Now these are two-wave, now I have two observations on each one of these two groups, the people who go from work to work and not work to not work, and that's what those two lines are. You can't really see very much, so I'll put these in a different graph using changes. So these show the two-wave changes of people who, according to their transition from work to work or not work to not work. And what you see is that the people who transit from not work to not work not only had lower scores to start out with, but they have greater declines because the blue line is the transition for people who go not work to not work, are below the red lines. And so the difference between those two, if we were to integrate this up, in fact, that's the next slide, will show a diverging difference between these two groups. And this is kind of a little bit of, this is certainly consistent with the idea that work is good for your cognition. The people who are transiting from work to work have slower declines than the people who transit from not work to not work. So you can integrate this up. These are cross-section scores and simulated scores, where the simulated scores start out at the same level at age 51 as the actual, but then integrate up these rates of change, and so you're controlling for selection on levels by doing that. And you can see, especially for the people who transit from not work to not work, that the lines are quite different. The cross-section line is basically flat. That is the third line from the top, or the second line from the bottom. The green line is the simulated line for not work to not work. And you can see that people who remain in not work, controlling for the original levels of cognition, actually experience fairly substantial declines in cognition, more than those people who remain in work. Again, you know, that's kind of quantifies it. But you can see by the time we get down to age 68, the difference between the simulated and the not simulated is quite substantial. And the cross-section is caused by people leaving work who have higher cognition scores than the people who are not in work, holding up the right side of that line. That's why that happens. But the simulation takes that out. Okay. This is a change in scores by labor force participation, work to work versus work to not work. And for this, not nearly as much difference between those two, but people who transit from work to not work have a slightly higher decline in cognition than people who transit from work to work. Not large, but it's there. Okay, so a summary of that is that people who go not work to not work have lower levels to start out, and they have greater decline than people who transit from work to work. People who transit from work to not work had lower levels while they were still working of cognition, and slightly greater decline when they transit to work compared to people who go work to work. Now, okay, well, that's what happens on the cognition side, and then I thought it'd be interesting to do the same thing on the health side. So, of course, value self-rated health, the simplest thing there is, and I'll just score these as on a 1 to 5 scale. If you look at things like the fraction in fair or poor health, you kind of get the same thing. So this is what I'll do here. So this is the scores according to the same groups that I started off with on the cognition. The top line are people who transit from work to work. Bottom line, people who transfer from not work to not work in cross-section. And you see the same thing at age 51. The people who are working are much more healthy than the people who are not working. The line for work is basically flat. These are cross-sections. And as we'll see, the people who are less healthy are leaving as you get out to the right-hand side. The cross-section for not work to not work actually has a positive slope, and that's because all these more healthy people are leaving the work state and joining the non-work state. That's one aspect. And the people in the non-work state who are in worse health die and leave the sample. So there's a lot of compositional changes here that are leading to these cross-sections, and should obviously make us wary about making anything from the cross-section. So here's the same thing, except the middle line is now people who transit from work to not work. And again, just as in the cognition, the people who transit from work to not work are less healthy than the people who transit from work to work, but they're more healthy than the people who transit from not work to not work, explaining that compositional change. And these, again, this is the transition from not work to work, and these people are now in the middle. Again, this would kind of be an interesting group to follow up, but I don't want to go into that now. Okay, so now now I have 4 lines, and these the top lines are wave T and wave T plus 2, wave T plus 1 scores for people who transfer from work to work, and you see those are high. but declining at every age, because the second line, the bottom line, is the wave T+1 cognitive score, and the top line is the wave T cognitive score. So these are true panel comparisons. And on a graph, it looks like this. The people who transit work to work, in this case, actually have a larger decline in health than the people who transit not work to not work. And these are panel comparisons. I have no good explanation for that. Again, if you simulate the trajectories, the top one is the cross-section work to work. The green line is the simulated, and so if you hold constant levels, mixing because of levels, then you get a fairly reasonable sharp decline in health of people who transit work to work. And really very different is the red line is the cross-section of people who transit not work to not work, but the blue line, bottom blue line, is the simulated, and so it shows that in fact the not work to not work people have declining health also. Okay, so I've been given the cutoff by John, so I'm just going to go to the summary of health. And basically, it kind of looks like the same summary as the cognitive. The summary is the relationship between work, retirement, and cognition is about the same as the relationship between working, retirement, and health. And that is going to be a problem in understanding causality. Turning now to the result of this paper, I very much like classifying jobs as to their cognitive complexity and mechanical demands. I think this is really a good thing to do and a really good step forward. They found greater decline when retiring from low cognitive jobs, similar to the results in a recent paper by Gwen Fisher, who's here somewhere in the audience, and we'll be talking later. And greater decline when retiring from highly mechanical jobs. One thing I would like to see are what are the characteristics of workers who are in those jobs, or those lower SES people who may be associated with greater health shocks and more severe health shocks. So getting back to the framework of the regression, have we adequately controlled for confounders? What about gamma? My conclusion on this is an important first step. It would be nice to think of an IV strategy before taking these too seriously as causal.
So I think given that it was the first paper, we'll give an extra 10 minutes. It's too sharp. There are questions. Now's the time. Wait for the mic. Give your name.
Okay. I'm Barbara Boberg from the Government Accountability Office, and so we're always thinking about policy implications. I find myself, as I get older and I hear these presentations, I can't help but take it personally. So I'm sitting here thinking, oh my God, I have to work forever just to sustain cognitive ability. But I was wondering, if you were going to talk to policymakers, what would you tell them they ought to think about when they see these results? I mean, it is an argument for encouraging people to work longer. Of course, they would have to know that this was going on. But I just wondered, so what would be the next step from a policy perspective, do you think, Bob?
Well, I think if it, I mean, I wouldn't want to disagree with Mike and his worries about sort of causal effects, but for the moment, let's suppose that we accept these effects as causal. What they do suggest is that this very old idea of use it or lose it is not totally wrong. That is that one should remain engaged. I could give. I mentioned at the very end. I looked at a little bit of data on the non-market side, and what you see is, for example, if you look at television watching, people who are in the lower groups spend an awful lot more time watching TV than the people who are in the upper education groups. And the changes in television watching, once retirement occurs, are also quite large. So it looks like there's some behavior that's going along with this. Another thing I happened to look at for reasons I won't go into, that was the fascinating topic of boredom. and what you see is that the low education and low work status people tend to be in their lives before they retire much more likely to be bored than upper educated people, and then that tends to get worse when retirement's taking place. So it seems to me that the kind of basic message is that leading a life that is more stimulating is good for you, and that people should maintain engagement.
So you may have answered this just now. This is John Chauvin. If you look at retirement, some people have quite active retirements. They volunteer and so forth. Other people watch TV all day. Have you looked at, what you do in retirement and how that affects cognitive decline?
We have not. This group has not yet looked at that. I know that Don has done some work on that. I don't know if you want to say a word on like volunteering.
There's a fairly robust literature that's looking not specifically at cognition, but on various aspects of health that suggests that engaging in volunteer behavior after retirement maintains health, has a positive health effect, and it suggests a causal relationship. Yeah.
There's a little caveat to that unfortunately the volunteering populations are highly positively biased populations, and there's a shortage of systematic comparisons that really have good matched controls. And so I think we are only starting to really understand what volunteering or other leisure time activities do or not do. Can I add a question? I was wondering, I couldn't quite follow, Bob, when you were showing your results, how much of the results were really longitudinal. The one thing that worries me also in your very nice discussant statement is that we know that there are major cohort differences in terms of intellectual functioning, and most likely also in aging trajectories, cognitive aging trajectories. And so I was wondering whether you had a chance to look at that.
So we controlled for age. I don't think that we controlled for cohort, and so that could be that would be a thing that we should do. The results are longitudinal in the sense that we're taking differences in
for the 6
scores
years
over time, so that to the extent that there's, and actually just to correct it slightly, what we call treatment effects there are actually 6 treatment effects. There's an effect that has to do with whether or not you're retired, but there's also an effect about which occupation you're in. And there's an interest, actually what I think is an interesting issue of scaling on these things. We did some calculations of test-retest data, and from that could calculate sort of get rid of the noise part and know what the sort of standard deviation of quote-unquote true cognition might be. And when you scale things in that way, you can actually get sort of what would be the change in the percentile of the person. Say you think of it as a normally distributed variable. The change in the percentiles of people, and that turns out to be some fairly large percentile changes if you're thinking of it as relative to the group that you're in. So if we thought of this group as a group, then we'd have a high mean to start with of cognition, and we could say, well, how big was that change? On the other hand, I need to think this through. If we thought of this group and we had like a 1 standard deviation in the population, and this group is already 2 standard deviations above the mean, it would hardly they'd still be the smartest people in the room. So I think one of the things that needs to be done more, and has not been done much in at least the literature done by economists, is to think about what's the what is the effect size, and how would you cast that effect size? What does it mean? Are these large effects or small effects?
Somehow it occurred to me that Kenneth Arrow is still the smartest guy in the room, usually when he's there. I think we should move to the next paper. Thank you.